This lecture is a review of the evolution of technology over the past 20 or 30 years, where we look at the trends in technology so that we can understand the environment for computing and processor development today and put in context what's happening in technology today. So in this topic, we'll cover the trends in power. We'll understand why we have multiple cores in most of the processors today. We'll talk about SPEC, that is methodology used to measure performance of CPUs, and we'll discuss Amdahl's law. Let's start with a review of what we call power trends. Power trend is the evolution of processors over time viewed from the point of view of power consumption of these processors. And the reason to focus on power is that the limiting factor for performance and for speed in processors is power. Many years ago, there was a great concern that physics and materials engineering would be the main factor is slowing down processors. And what history has shown is that power consumption and power dissipation is what have led to the processors stop getting faster every year as they used to. And what we have here is a graph that will talk about CMOS technology. So first, let's make sure that we understand what is CMOS technology. Let me change to the other screen here. And so CMOS stands to complementary metal oxide semiconductor, and is the technology that is predominant in the creation of integrated circuits that we use today. So IC stands for integrated circuit. So this graph will show two curves in the same plot. The scale on the left is for the clock rate, and the unit for the clock rate measure here is megahertz. And the scale on the right will be the power consumption, and that is roughly the steady power consumption when the processors are performing at their nominal speed. And we have on the x-axis, we're going to have different processors and the year in which they were released. So the idea here is to look at the trend in power consumption. But before we do that, let's review a relationship that exists between the power that's consumed in a processor and the proportions of the power. So there is something called a capacitive load that's a characteristic of the processor that will determine the power, and power will have an evolution that's linear with that. Then there is another factor that's the voltage, and the important thing to note here is that power is proportional to the square of the voltage. So if I decrease the voltage in which I operate as an integrated circuit, I get a square reduction in the power. Or in the other way, if I double the voltage, I will consume 4 times as much power. So the voltage has a significant influence in the amount of power that a circuit consumes. And then the third factor is frequency. And the relationship between power and frequency is linear. So doubling the frequency will double the power that's consumed. So let's look at the evolution when we start a long time ago. We start in 1982. In 1982, Intel had a processor 8286. And what this graph is showing is the clock rate. The clock rate of that processor released in 1982 was 12.5 megahertz, and the power consumed was in the order of 3.3 watts. Your typical a bright light bulb consumes 100 watts. Um, so this gives you a sense for the amount of power consumed by the processors. And 100 watts is quite a bit of power. You just have to put an incandescent light to burn for a while, and then try to touch that light, and you'll see that it can get very hot. Now you have to consider that amount of power being dissipated in a very small area, that is the area of the chip of where a processor is. In 1985, 3 years later, Intel had the 18386, and the frequency had gone to 16 megahertz, and the power was still 4.1 watts. In 1989, with the 486, the clock rate had gone to 25 megahertz, and the power consumption had increased a little bit. And then in 1993, the Pentium had a clock rate of 66 megahertz, and the power had increased to 10. If you look at the relationship that you see at the bottom, where the power grows linearly with the frequency, you can see that the frequency is higher, is growing more or growing faster than the power consumption. So we're going to talk in a minute to explain what's going on there that has led to that. And then we have a 200 megahertz processor in 1997. We are now at 29 watts. By 2001, we were at 2000 megahertz, which was 2 gigahertz, with a power consumption of 75 watts. So we are getting close to the power consumption of a bright light bulb. And around 2004, the frequency had reached 3.6 gigahertz, and the power had reached about 100 watts. And from there on, what happened over time is that the frequency has not increased much. It's common to have frequency between 3 and 4 gigahertz, which would be 4,000 megahertz today. And the power consumption has since then stayed around 100 watts or so. The main reason for that is that it is very difficult to cool a processor that is dissipating much more power than about 100 watts. And how come that we managed to increase the frequency so much without increasing the power as much? And what has happened during that time is that the voltage that in which we operate the processors has reduced over time. So we have seen about 1,000 increase in the frequency over that time, but the voltage has decreased between 5 volts to 1 volt. So today we operate most processors around 1 volt, and that is what has allowed the processors to increase their frequency over that period of time. The problem that we run today, and that is called the power wall. So during that time, the power consumption increased by about 30 times. And we run into what we know as the power wall, in the sense that we cannot increase the frequency anymore like we used to be able to, and like we'd like to do, because we have reached a voltage, reduced the voltage to around 1 volt. If we reduce the voltage much further than that, the noise, the environmental noise that we have that affects the chip would change the value of a bit between 0 and 1 with such a high frequency that might be difficult to operate the processor and to produce correct results. So this is the story of the trend between power and and frequency and voltage. So let me just skip this because it's a duplicate slide. What we have now is a different curve. This curve is trying to show the effect of the frequency on the power voltage curve. So if I have processors running about 500 megahertz, I can operate them at a lower voltage, and therefore I consume lower power. As I increase the frequency, I can no longer operate at the lower voltage. So there is a dependence also between the voltage and the frequency in which I can operate the processor. And as I operate it, the power consumption increases. And you see this trend when I get to 1 gigahertz, my voltage has to be slightly above 1. And then as I get at the higher frequencies, the operating voltage has to be higher and the power frequency increases. So this is the point of this curve, is to show that that the frequency also affects the voltage that I can operate, and there is a relationship between frequency and power. This is a graph that I extracted from the Chip Design magazine. This is another plot that's very classic. This plot plots a curve of performance. And the performance here is relative to a very old computer, a computer that's commonly used as a reference for performance measurements. That is the VAX 11780. And this plot will go from 1978 to 2006. We could have more up-to-date plots. We can find some of those in the web. But what we're going to see is that after 2006, there has been pretty much a plateau in the evolution of performance. So what we have here is in the first about 10 years, starting 1978, we have a sharp increase in performance. And notice that the scale in the y-axis is logarithmic. So this straight line that we are plotting here in the evolution of performance in these different processors actually is an exponential growth during that time. So we have an exponential growth in the performance of processors happening, and for a time, and that's common for human nature, when seeing an exponential trend, is to speculate that the exponential trend will gonna go forever. For a time, there was that expectation that the power or the performance of processors would keep growing exponentially forever. And it did happen for quite a long time. You see that we are in 1998 and the growth is still exponential. And then when we get to the year 2000s is when we are getting to the ranges of frequency of the processors that is leading us to the power wall, where we don't no longer see a growth in frequency, because the processors are now dissipating around 100 watts each, and we have reduced the voltage as much as we could. We can no longer increase the frequency, and therefore we cannot easily increase the performance. So it was around 2005, 2004, 2005 that the multi-core revolution happened. That is, companies could no longer build faster processors, so they decided to insert multiple processors in one chip. So this growth has constrained because we are constrained by power. Instruction level parallelism also is a limitation. We'll talk a little bit about that in the next slide. And memory latency, that is the time that it takes to bring data from the memory to the processor, is too long and limits performance. So that limitation in the performance of a single processor led many companies to start fabricating processors with multiple cores in them. And that was a risk bet from the companies, because at the time it was not very clear that we'll be able to use all those cores. And still today, in many of our computers, there is a subutilization of the cores in many situations that is due to programming. And programming parallel processors is much more difficult than programming a processor that contains a computer that contains a single processor. So here we have a top-level schematic for a RISC-V FE 310 processor. This is the schematic for the inner design of a single processor. In a single core processor, doesn't mean that each instruction is executed one at a time. I know that when we do our performance calculations in 229, we do assume that each instruction will take, for example, 1 cycle or 3 cycles or 4 cycles, and we work with the mental model that there is a single instruction executing at a time in the processor. This is a simplification. It's a necessary simplification for us to understand the basic concepts of computer architecture. However, as we advance in the topic, we're going to start understanding that actually there are multiple instructions that are being executed at the same time. And especially when we reach 429, that's the 40-year computer architecture class, we're going to explore in much more detail how processors actually execute instruction. But one thing that is relevant for this discussion is that there is something called instruction level parallelism. Instruction level parallelism occurs when the hardware executes multiple instructions at once in the same cycle. And there was hope also sometime in the past that instruction level parallelism would keep growing, in the sense that would be able to keep increasing the number of instructions that are executed in a single cycle. That run into a limitation because of data dependence and control flow in programs. And again, we will explore this in more depth later in this term and also in Fortune. Instruction level parallelism is completely hidden from the programmer. It is the compiler and the hardware that will take care of executing programs that the programmer wrote to be executed sequentially. And between the compiler and the hardware, the system will discover that some of those instructions can actually be executed in parallel. But it requires no effort from the programmer to make ILP happen. Another alternative is, as I already mentioned before, multiprocessors. Here I have a picture from the quad-core AMD Opteron. It's a 2007 vintage processor. All processors that are produced today are multi-core processors. And in this picture, you can clearly see on the four corners are the four processors. And that area in the center of the figure that's more homogeneous is memory. And this area here is most likely networking and other services. This is a multi-core microprocessor. In a multi-core microprocessor, you have to explicitly program it to execute programs in parallel. This parallelism can happen inside a single application, in which case either the programmer has to specifically state that certain actions or certain computations can be done in parallel, or the compiler can discover automatically that there is parallelism in that application. And it can be done also at the system level, where the operating system can schedule multiple programs to execute in different processors at the same time. Parallel programming is hard to do. You need to program for performance. You need to worry about load balancing, because if you have one of these processors doing one part of the computation that takes a long time and the other processors are doing computations that take much less time, you're going to have a subutilization of the system. You also have to optimize for communication and synchronization. What that means is that the different portions of your application may be accessing the same data, and they may need to communicate results between each other. When they are accessing the same data, you need to very carefully synchronize the accesses so that a given statement does not receive an outdated or stale data. We'll cover again later in November some more of these concepts, and also these concepts are covered with much greater detail in Fortune 9. The next topic that I want to cover in this lecture is the problem of how you measure performance of a computer that contains a processor. And there are different ways that you can measure performance, but companies wanted to have a way to measure performance that would be fair. The idea is to have a methodology to measure performance such that all the different competing companies will have to agree on that methodology, and every time that you measure performance, you have to use the same methodology. So an organization was created. It's about 30 years ago. It's called the Standard Performance Evaluation Corporation, or SPEC. SPEC was founded in 1988, and it has today more than 100 members, organizations, and associates. SPEC is a not-for-profit corporation that has several different groups. There is one group that's the most recently created group. It's now about 15 years, is the research group. There is a graphics and workstation performance group. There is the high performance group, or HPG, and there is the operating systems group, open systems group, or OSG. And inside OSG, there is a working group called the CPU working group. It is the CPU working group that is the most relevant for us in this discussion, because that's the group that creates the SPEC CPU benchmarks. There have been several versions of the SPEC CPU benchmark over the years. The most recent one is the SPEC 2017 CPU benchmark. So the CPU benchmark, SPEC CPU benchmark, is a set of programs that have been selected as representative of what people usually do when they are using computers. The CPU benchmarks are intended to measure the performance of the CPU. So by design, they are not programs that do a lot of communication. So they are not programs to communicate over the internet, for example. They are not programs that access lots of data in database. They don't do a whole lot of input-output operations. These programs are intensive CPU computing programs because their intent is to measure the quality or the performance of the processors themselves. A number of years ago, when the SPEC research group was created, I was involved in the creation of the SPEC research group. I was one of the founding members. And some years later, I was invited to put my name forward to sit in the SPEC board of directors. And I was elected, and I have been serving in the board of directors for many years now. To give you an idea of this board, there are 8 members around the table when we sit around the table. And those are the companies that are represented today in the SPEC board. The members, the directors, are actually the people that are elected, but only one member from each organization can be in this board. And I am the only member of the SPEC board of directors that is from academia. So in their view, I am there to try to represent and be a voice for the academics that use extensively the SPEC benchmarks for research. So the SPEC benchmarks are used by companies. So a company can measure the performance of a new processor that the company will release or has released, and can submit those measurements to for review by, for example, the CPU working group. And also the results are reviewed and approved. They will be published in the SPEC website. And once they are published in the SPEC website, the company can use those results in their official or their public advertising for their product. If you look at advertisements in the past, you're going to have things like Oracle making a statement about being better than IBM, and other times IBM making statements that they are better than Oracle based on the SPEC results that are published and are vetted by all the other companies. So with this background, so there is are some of the organizations that are part of SPEC. And let's talk about the SPEC CPU benchmark. That is the one that is more relevant for this course because we are studying processors. The SPEC CPU benchmarks is a collection of programs that are used to measure performance. They are expected to be typical of actual workloads. I say expected or supposedly because it's a decision, is a judgment made by a group of people, and it would be impossible to actually have an oracle that says this is actually the set of programs that will represent the use, and the use of computers is very varied. Different people make different uses of their computer. But the idea is that each one of these programs is standing for an entire class of programs that have similar characteristics. So SPEC developed benchmarks for CPU, I/O, web. There is the Java benchmarks. There are graphics benchmarks. There are all kinds of different benchmarks that are developed for SPEC. So prior to the SPEC CPU, there's a type in the slide, should be CPU, not SPU. Prior to the SPEC CPU 2017, the previous release was in 2006, and prior to that was in 2000. The time that elapsed between these releases is the time that it takes to select the programs. And right now there is an open call for programs for the next release of the SPEC CPU benchmark. So it takes years for the group of companies that sit around the table to select and then decide and vote on which programs will be part of the SPEC CPU. As I said before, these programs do not do many input-output operations. The focus is on CPU performance. The measurement of performance in the SPEC CPU is normalized relative to a reference machine. And the idea is to pick a reference machine that will be slower than any machine that could be currently measured with that benchmark suite. And so that when I do a relative performance, the relative performance to that machine will always be greater than 1. The SPEC, so there is this desire to have a single number, especially because the results of these measurements will be used for advertising. Companies wanted to have a single number that they can say, I got this SPEC number for this processor and you got that SPEC number for your processor, therefore I have better performance. And so this number also, there is a desire that this number be, if the number is bigger, your processor has superior performance. So the summarization of the results is the geometric mean of performance ratios. The idea is that you compute the product of the execution time ratio. Execution time ratio is you take the execution time of the program in your machine and you divide it by the execution time of the program in the reference machine. That will give you a ratio. You make the ratio, you take the product of those ratios for all the programs in the benchmark suite, and then you take the nth root of this product, and that gives you the geometric mean. In 2006, and again it will be the same thing in 2017, there is an integer and a floating point benchmark suite. And here I have a sample of SPEC. Again, there is a typo in the slide. I apologize for that. No, this is correct, actually. SPEC CPU 2017 int is a publication result, so there is the link there, and that illustrates to you how results are published in the SPEC benchmark suite. So in the SPEC benchmark website, when you publish a result, you have to provide full specification of your machine, so that people can know which version of your processor has been measured, how much memory it had, etc. So here is a typical result published. So it will show how many threads are executing, and then will give you the number of seconds that it took to execute each one of the programs. So that's the second rate, the second column. And then it will give you the ratio in comparison with the base machine. So the higher the ratio, the faster the program is. And it will give you the number of seconds, it's the number of seconds in the base machine and the ratio for each one of them. So the SPEC ratio will be the reference time divided by the execution time. And the SPEC speed for this machine for the base, speed base means that you cannot be turning specific flags in your compiler, for example, was 8.98. So summarizing, oh no, there is another thing that I want to talk about because it involves us here at the University of Alberta. So as I was a member of the SPEC research group and also a member of the board at the time, I had a problem. And the problem was, and that was what motivated my involvement in SPEC, is that in my research community, that is the compiler community, but it also happens in the computer architecture community, there's extensive use of the SPEC benchmarks to measure the results of research. For example, to state how much faster a machine is compared with a machine, how much faster your machine will get when you do a certain optimization. So the problem is that often learning is used in this optimization in the sense that we run a program first and to observe the behavior of the program, and later we do transformations to the program based on what we learn, and then we evaluate. The problem with that is that if you use the same workload, that which is the same input for the program, both to train your compiler, for example, and then to evaluate how well you're doing, you're cheating. In learning, we cannot use the same data set to learn and then to evaluate. And SPEC CPU has traditionally published just a very small number, just 2 or 3 inputs for every benchmark. So we got involved here at the University of Alberta with a team of students that worked over 3 years with the SPEC CPU group to create alternative workloads for these benchmarks. And these workloads are now published under the auspices of the SPEC research group. And so they appear in the SPEC research group website. And we also produced a paper that describes these workloads. It's called the Alberta Workloads for the SPEC CPU 2017 Benchmark Suite. This paper was published, I presented it actually at this conference called ISPAS, that's the International Symposium on Performance Analysis of Systems and Software, which took place in Belfast in Northern Ireland in 2018. And I want to call your attention to some strong connection with 229 here. So one of the things that I have been doing for a number of years now is I get to know students when I'm teaching 2 to 9. And at the end of the term, students that have done well in the course and that have interest in following with research or development sometimes, um, can get involved and engaged in my research lab in the summer. So most of the work done for the development of these Alberta workloads for the SPEC CPU 2017 benchmark suite were done by students in the lab during the summer. And I want to highlight to you here that of this set of authors that we have here, we have a few students such as João Hoffman and Kayan Benedict that were visiting students in the lab from the University of Campinas. Edson Borin is a professor at the University of Campinas. But the students that I just highlighted there were former 2 to 9 students, just like you. Those were students that got engaged in research and end up doing a very significant collaboration to the release of these Alberta workloads. So the last topic that I want to cover, and I apologize, I know that this lecture is getting a bit long, is Amdahl's law. And Amdahl's law is a very simple principle. The principle of Amdahl's law is that if you improve a single aspect of a computer, that improvement does not lead to a proportional improvement in the overall performance of the computer. Another way to state Amdahl's law is that you only can improve what you change. The things that you cannot change, you are not improving. So what's the relevance of that? The relevance of that is that that time that's not affected by your change to the system will drag down your improvement. Um, the time of the improved version of your system will be only the time that was affected by the improvement divided by improvement factor plus the time that was not affected. So, for example, if before I did anything to my system, this was the time that it took to do an activity, for example, to execute a given program in a computer. And then I go and I do an improvement to the system and I say I'm going to make the memory faster, for example. So there is only one portion of the operation that will be one proportion or one percentage of the operation or the time, the original time that will be affected. And there will be all that other time that's not affected by my change. So if I wanted to have an improvement factor of 2 afterwards, so it means that I got my affected time to be half as much as it was before, then my new time will be the time that never got affected by my change plus that improved time for the affected portion. So this is the affected portion of the time, and then I have all this time that was never affected by my change that will limit how much I can improve the system. This is something that's not only good for computers. You should take this to life. Oftentimes, people come to you and they say that they're going to make something twice as fast or twice as bad or twice as cheap or any other factor when they are only affecting one small portion either of the cost or the time or the power consumption. So whenever someone comes to you with a proposal that they are going to do an improvement to something and something, this is a principle that you can take to your working life later. You should always ask, but how much of the total cost or the total time you're going to be affecting by your change? Because we have to consider all that portion that's not changed that will be dragging us down. So here is an example so that you can illustrate the use of this very simple law. This law has a name, Amdahl's law, because Amdahl was the first one to state this law. And let's say that I have a program that takes 100 seconds to execute and that multiplications account for 80 seconds of that time. The question is, how much improvement should I have in my multiplication performance to obtain a 5 times overall improvement in this application? So what I have here is that the total time is 100 seconds before I do anything. And 80 seconds are spent in multiplication, and that's the portion that are going to be affecting with my change. So 5 times improvement implies that the new total time will have to be 20 seconds. So the only way that I could do that is by doing no multiplications whatsoever. If I can do that, I can get that performance. But otherwise, I cannot get this program to run 5 times faster only by changing multiplication. So this cannot be done, and that is one application of Amdahl's law. Just to illustrate how Amdahl's law can quickly let you figure out what are the limits of the improvement that you are making to a system. Let's talk about some pitfalls in performance measurement. So MIPS is commonly used as a performance metric. MIPS stands for millions of instructions per second. But the problem with that performance metric is that if you are only counting instructions per second, then you are not accounting for differences in the instruction set architecture between the computers. You are not accounting for differences in the complexity between those instructions. For example, BIPS is the instruction count divided by the execution time times 10 to the 6. If I replace execution time by its expression, that is the number of instructions executed times CPI divided by the clock rate, what MIPS is actually measuring is the clock rate divided by the CPI, that is the average clock per instruction. And the issue is that the average number of clock per instructions will change depending on the program that you are executing, depending on the CPU. So we need to be very careful when we are measuring performance so that you use a metric that makes sense for the application that you have. So finally, concluding this lecture, what we review here is that cost performance is improving because of underlying technology development, but we saw that there is a limit, and the limit is because of the amount of power that we dissipate. We saw that there are hierarchical layers of abstractions in both software and hardware. We didn't see this all in this lecture, but we have been discussing this throughout the course so far. Instruction set architecture is the hardware-software interface that we have. And the best way to measure performance is by measuring execution time instead of measuring things like the number of instructions per second. And to measure performance through execution time, often we use standard benchmarks such as the SPEC benchmark suite that I talked about. And power is a limiting factor for increasing performance, and the limitation, because we cannot dissipate more power, therefore cannot increase frequency, led to the development of what we call the multi-core revolution, that is the use of parallelism to improve performance. Thank you for watching. This was a long lecture, I know.